Okay, hello. The students, Ben, as usual, asked about, it's a good thing that he asked, asking about, and not just Ben, but some of the other students asked about 5.2 with all of the summations and stuff. I generally don't put those on the test, but I think it's important to learn this because we keep going on. They try to make things more and more rigorous. And not only that, you can get integrals to do a lot of different things, not just finding area underneath curves, right? You can get it to add up vectors over a surface and just add up anything you can imagine. So it's very powerful. There'll be special types of integrals and things like that later on, and a lot of physics is connected to it. So the better you understand how these things work, the better off you're going to be if you end up having to deal with a lot of different types of summations and integral formulas. Okay, so that being said, chapter 5 is all about basically just finding area underneath curves. This problem was huge for centuries. Okay, I think it goes all the way back to the Greeks, and even farther probably back to the Egyptians, where they were just plotting, their land property and things like that. But the Egyptians were more into triangles, obviously. It wasn't until I think the Greeks that you actually started worrying about curvy type regions, okay? And what you're seeing is just the culmination of hundreds of years of progress for which you were not present, okay? So it may seem like a lot, and it is. Okay, that being said, let's look at the first problem I saw in the book. G of x equals 2x squared, and I hope the stupid microphone, you can hear me. Okay, I missed my whole intro. Oh well. The first problem I was looking at, 2x squared minus x minus 1 on the interval from 2 to 5 with 6 rectangles. Okay. And what does that mean? That means we're approximating the area under this curve from 1, 2, 3, 4, 5, from the point 2 to the point 5. Okay, this thing's a parabola. It goes way up. So if I'm going to go by 5s, 10, 15, 20, 25, 30, and I ran out of room. So I'm going to put a couple extra ones in here. So this is 5, 10, 15, 20, 25, 30, 35, 40, 20, 25, 30. And I went ahead of time and figured out all the values. It says we need 6 rectangles. So what does that mean? That means here's our interval from 2 to 6, and I want 6 little subdivisions in there. So if you put in tick marks like this, and usually I just kind of eyeball it. When I first started calculus, I would just say, all right, I think this will be enough, right? So 1, 2, 3, 4, 5, 6. There should be 6 intervals in there, and that's what you want. And you can tell how long the intervals are just by taking this 2, 5 interval. So you just take 5 minus 2, the endpoints, the right endpoint minus the left endpoint, and divide by 6. Okay, so that would be 3 over 6, which is 1/2. And that's the delta x thing they talk about. Okay, so we're moving by delta x every time. So I'm going from 2 to 2 plus delta x. So 2 plus 1/2 is 2.5, or if you'd rather, 5 halves. And then 5 halves plus another delta x will be 6 halves, and so on. 7 halves, 8 halves, 9 halves, 10 halves, which is the same as 5. Okay. And then I'm going to plot the points. I already evaluated them in my calculator earlier. So f of 2 is at 5. Or it's g in this case. G of 5 halves is at 9. Okay. G of 6 halves is at 14. G of 7 halves goes up to 20. And G of 8 halves is 27. And then G of 9 halves is 35. And G of 5 is like 44, so up here somewhere. It should be a parabola type shape. It's not exact because of okay. So anyways, we're looking for the area underneath that curve. We're looking for this area here. Okay, and that was the rave back in the days. Everybody wanted to figure out the area underneath the curves, and they were killing themselves trying to do this. Okay, all right. So how does the book want you to do it? So they just want you to do the beginning steps first. And there's two ways you can get approximations. And the spiel will be that actually you can use anything you want in this interval in order to get the heights for your rectangles to do a so what are they doing? They're doing an approximation of the area underneath this curve using rectangles, okay? But you can use different rectangles. You don't have to use the rectangle based off of the left-hand endpoint, which would be this rectangle. Okay, so left-hand endpoints versus right endpoints. So this is your left-hand endpoint, and this is your right-hand endpoint. Okay, and they're going to build the rectangles based off either the left or the right. You can use any. It turns out you can use any point in this interval, but this is the way they're going to introduce it to you. Okay, so if you use the left endpoint, the first rectangle, its height will be based off of f of 2. So let me just write, I'm doing left endpoints. Okay, so my first rectangle, I need the area for that. I'm basing the height off of 2. So it's going to be f of 2 times the length of the base, which is always change in x, which we were given as 1/2. Okay, and then plus this next rectangle, and again I base it off the left endpoint. Okay, so that will be f of 5/2 times 1/2, and you continue on doing that until you get to this last interval here, and the left endpoint is the 9/2. Okay, so we need f of 9/2 times 1/2. Okay. Okay, and then if you plug that into your calculator, you're going to get 55, right? So you plug the 2, and this should be, sorry, let me just call this f of x rather than g of x. Okay, so what am I doing? There goes my notes, and hopefully that won't be an issue. What am I doing? I'm plugging 2 into this function, so 2 times 2 squared is 8, minus 2 is 6, minus 1 is 5. So I would have 5 times 1/2. And then I plug 5/2 in there, and then I add them up. I get 55. Okay, so that's the left endpoint. The right endpoint, instead of using these points, I'm going to use, guess what, these points. So I have this one, this one, this one, this one, this one, and this one. So the sum is very similar. It's just instead of starting with this as my endpoint, I'm going to use this as my endpoint here. Okay, so f of 5/2 times 1/2 for the area underneath this rectangle. Okay, so this will be f of 5/2 times 1/2. And then I'll move over to this rectangle, and its height will be f of 6/2. Okay, so f of 6/2. And you notice there's not much of a difference between the left endpoint and the right endpoint sums, right? This guy is right here. This guy would be right there. Then you go plus dot 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 plus. And then the last one, I actually do use 5, right? Because the right endpoint would be at 5. So my last rectangle would be up there, okay? So then it would be f of 5 times 1/2, and if you added all that together, you would get 74.5. Okay. You could also do midpoints too, but in general, it'll turn out that you can use any point you desire, and when you take the limit later on, it's sort of letting this distance go to 0, so you would have this point, this generic point in the interval, and it's kind of going to get smushed when you take the limit, and that'll be, you know, whatever it is. Okay, so hopefully that helps a little bit. Okay, and in general is where we want to go, right? And I think the computational aspects of that are very difficult. In general, what we need is a sequence of numbers for these functions. Okay, because in general, what we're going to want to do is use n rectangles. So the question becomes, how do I do this in general with n rectangles? And then I have to take the limit of these sums, right? So I have to be taking the limit as n goes to infinity of the sum of f of whatever times change in x as where I varies from 1 to n. Okay, so I need to figure out what the heck kind of goes in here and basically it's a formula that's going to produce these numbers 2, 5 halves, blah 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 blah. And how do I get that formula? Well, that formula is from arithmetic sequences that you learned in pre-calc. Okay, so arithmetic sequences. And we could work with that example we just had. The first term we want is 2. And then the second term we wanted was 2 plus 1/2, right? Which is equal to, we could rewrite it as then 4 halves plus 1/2 is the 5 halves that we had in our interval. Okay, so a sub 3, well, a sub 3 is just this previous guy plus another half. You could write it plus 2 plus 1/2 plus 1/2, okay? And that'll end up being 7 halves, of course. But look what's happening is you're getting this kind of pattern. The next guy is 2 plus 1/2 plus 1/2, a sub 3, the a sub 3 position, right? So your a sub 3 is right here. To get to a sub 4, what you need to do is add in another 1/2, right? So a sub 4 is just a sub 3, and then plus another 1/2. What am I getting at? Well, I'm getting at a formula. Look, I could rewrite 2 plus 1/2 plus 1/2 plus 1/2 as 2 plus 3 1/2, right? And then for a sub 5, I could rewrite that as 2 plus, well, from this pattern that's kind of, you know, there's 2 1/2, there's 3 1/2, so, oh, it's 4 1/2, right? And in general, I can produce this formula a sub n, which is going to be 2 plus, well, if this is 4, I need a 3. If this is 5, I need a 4. So if this is n, I need an n minus 1, and then times 1/2. Okay? This is the formula for arithmetic sequences that you were given back in pre-calc. So a sub n is going to be equal to 2, or in general, a sub n is going to be equal to the first starting point, okay, that was 2 for us, plus an n number, n minus 1 number of these moves, right? So you're going over by 1/2 each time. The pre-calculus book gave that the letter D. If you use the Blitzer book, they had it letter D. Okay, so this is the arithmetic formula, and this is the formula that's going to be going in to these functions, okay, that we're adding up and using to approximate the area underneath these curves. Okay, so that's the answer to this question right here. What goes in there? Well, it's going to be kind of this thing. But there's an issue, right? There's left-hand and right-hand endpoints. So we need to investigate those a little bit more in detail to iron it out. Okay, so for the left-hand, or sorry, I want to start with the right-hand endpoints, because this formula is usually the formula I don't want to use because it's too complicated, right? So I have a to b, and then I'm moving by change in x every time, and then dot, 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 and then this, okay? So there's a bunch of junk happening in the middle, right? My formula for the points, I usually use a sub I, but because I've used a as this first endpoint, I'm going to use p instead, okay? So the formula for which point I'm on, so the formula for the point that I need in order to put into this function is p sub I equals a plus, instead of n, I'm going to use I, because we're using n for something else. Okay, so I use I minus 1 times change in x. Okay, and we ask ourselves, does this work? Okay, in general, does this work? So look, p sub 1 is, well, that's going to be a plus 1 minus 1, which is 0, so that's just a. In other words, we're starting with the left endpoint when you use this formula. Okay, and then p sub 2 is going to be a plus a change in x, so that just moves you over by one change in x. And then p sub 3 is going to be a plus 2 change in x's, so that's going to give you this point right here. And then you keep on doing that until p sub n, which is the last one we want, and we don't want b, right? We want the one directly before b. We want this guy to be the last point we put into our function, right? Because if you look back at our example, if you're doing left endpoints, which is what we're doing right now, you don't end at the last number. You don't end at 5, you end at the number right before it, 9/2. So we don't want to end at b, we want to end at the one right before it. So let's see if we got that. Well, a plus n minus 1 times change in x, okay? And what is that? Well, that's a plus n times change in x minus change in x. What is n? What is change in x? Well, change in x is defined to be b minus a all over n, okay? And then minus change in x. And then these cancel, so I'll have a plus b minus a minus change in x. And then the a's cancel, and you're left with b minus change in x. Okay, so where is that? Well, here's b, and then if you go back minus change in x, you get to that particular value we want, which is p sub n. Okay, okay, so a is the same as p sub 1, and then this would have been p sub 2, and then p sub 3, all the way up to p sub n minus 1, and then p sub n is the last left endpoint that we need for our sum. Okay, so that's the whereabouts, and so the formula that we use when we want this general version for n endpoints is going to be, so for, what are we doing? The left endpoint sum to give you the sum of the rectangles is going to be f of this p sub I thing, which is a plus I minus 1 times change in x times change in x from I equals 1 to n. Okay, and of course we are asked to take the limit of that thing, and that magically gives us the correct answer for the area under the curve. Okay, that limit thing is very powerful. They didn't know about that for a very long time, and then somebody kind of dreamed it up, right? Okay, so that's the left endpoint. The right endpoint, this time the points that we want to pick for our right endpoints, and that was with the red rectangles here, we don't want to start at 2, right? This formula, we're not plugging 2 in first. We start at the right endpoint. So we're going to want this guy, this guy, this guy, this guy, this guy, and the last guy. So I need a formula to pull that off. Again, I'm going to use p sub I. I need, really, I want p sub 1 to be this guy here, right? So I want my p sub 1 to be this guy, and then p sub 2, p sub 3, all the way up to, this should be b, all the way up to p sub n, which I'm hoping equals b, okay? So this would be p sub n minus 1, p sub n minus 2, okay? All right, so let's go at it. So my formula, p sub I this time, well, I'm not starting at a, right? The starting place, so normally it would be a plus, I'm going to leave a little space because I need that, a plus I minus 1 times change in x, okay? That would normally be if I'm starting here, but I'm not starting there, I'm starting here. So where is that? Well, that's move a over by change in x. That point there is a plus change in x. So instead of starting at a, I'm going to start at a plus change in x, okay? And then this formula simplifies, which is why generally we'll use the right-hand endpoint when we're doing these crazy limit problems later on. So I'll have a plus change in x plus I change in x minus change in x, which simplifies to a plus I change in x. Okay? And we can check to make sure that works in the picture. All right? So p sub 1 is a plus 1 times change in x, which is where we want it. Right? And then p sub 2, whoops, so if I is equal to 1, it'll be 1 times change in x, so it'll be a plus change in x. And then if p is equal to 2, or sorry, if I is equal to 2, it'll be a plus 2 change in x's, which will be right here. Okay, so that will be p sub 2, and we're getting the right endpoints of all of our intervals. So this is the left endpoint, this is the right endpoint, right endpoint, right endpoint, and we want to end at b, right? So let's see if that happens. Is p sub n equal to b? So what is p sub n? P sub n is a plus n change in x's. What is change in x? Well, change in x is b minus a all over n. And then that's equal to a plus b minus a, which is equal to b. And we got it. Okay, it works. Great. So that's going to be our right endpoint formula. And in that case, then we have the sum of f of a plus I times change in x. Where is it? It's right here. Okay, a plus I times change in x times change in x from I equals 1 to n. All right, and this is the formula du jour. Okay, you could do the same process for midpoint. Let me just give you that formula in case you don't have it. So the midpoint formula, I can find where the heck it is on my notes. The midpoint formula is going to be the sum of f of a plus change in x sub I minus, I believe it's change in x over 2 times change in x. Okay, so I just built another sequence formula where instead of starting at a plus change in x or a, I start at this point right here in between, which would be a plus change in x over 2. And then I took that and I plugged it in for this portion of my formula, and then I was able to simplify that, and my simplified formula is this thing right here, okay, where this is maybe not clear, it's an I, all right? All right, so you have those formulas. Now we want to actually apply it to one of those ones where you have to do the limit. And again, I'm not going to do this to you on a test or anything like that. I mostly am I just worry about, can you do the antiderivatives, okay? This is great stuff, but if this is your terminal course, if you're never going to take calculus again, it's probably not that important, okay? Okay. So anyways, let's try a hard one, right? Let's try number 53. And I tried to show this one to, I think, Sujatha during my office hours, which you are more than welcome to stop by for on WebEx. Okay. Anyways, we want to find the area underneath this curve on the interval from 1 to 3, okay? Using this taking the limit, the taking the limit of the sum, right? Okay. So this is hard. This is not easy, and I have some of it done for me already in my paper, so I don't have to sit there half-hour foiling. Okay. So anyways, I need the change in x to pull this off, and the change in x is 3 minus 1 all over n. So it'll be 2 over n. And then I'm using the right-hand endpoint formula, right? Because that formula is easier, usually. Sorry, the left-hand endpoint is the one I want. Hopefully that's what I said when I was giving my little lecture there. Let me make sure before I send you off to be mowed down by the... so this is a formula we want. That's the right-hand endpoint. Let me just make sure that's right. This formula is the right endpoint. For some reason I wrote left in my notes. I must have screwed it up in my notes. It has to be the right endpoint. I mean, what are we doing? We're using the right endpoints, right? So, okay. Yeah, so I'm going to do this one that I was, okay, so I'm doing 53, and yeah, it's a bear, right? So I want to use my left-hand formula, the sum thing, and then I take the limit of that sum as n goes to infinity, as the number of rectangles goes to infinity, right? So I'm going from I equals 1 to n of f of, and now I put in my formula, right? So it's going to be a, which is 1, plus I times change in x, which I just figured out was 2 over n. Okay, and then times change in x, which is 2 over n, right? Okay, so as soon as you start doing this, you know you're in for the ride of your life. And you make one little mistake and you're out of luck, right? All right, so anyways, what do we have? F of this thing, so you have to take this thing and plug it into this thing here. So it's going to be 27 minus 1 plus, I'll just rewrite this as 2i over n cubed, and then times 2 over n. Okay, all of this stuff is inside the sum, and the sum going from 1 to n. Okay. All right, so I need to cube this thing out. And the way I did it was to find a common denominator. So let me write that here. N plus 2i all over n cubed, right? That's this thing here. I just made 1 as n over n, and then n plus 2i all over the common denominator of n. Okay, if you cube that out, and I'm not going to, actually, this is the part I have it written down. You'll get n cubed plus 6i n squared plus 12i squared n plus 8i cubed all over n cubed. Okay, so you have a lot of foiling and stuff to do. And then I'm going to plop it back into here. I need to, this minus this thing, I'll find a common denominator of n cubed. So this would be 27n cubed over n cubed minus this whole thing. When I subtract this whole thing, it'll be 27n cubed minus n cubed, which will be 26n cubed as your leading term on that polynomial. So let me just jump to that part. I have then 26n cubed minus 6i n squared minus 12i squared n minus 8i cubed all over n cubed, and then times 2 over n. Okay? And of course, we're taking the limit of this thing. Okay. You can distribute here. I looked on CalcChat and they don't, but you can factor this out of the summation symbol. The summation symbol is going from 1 to n. It's finite, so you can factor out any constants. And 2 over n is not dependent on I. It's dependent on n. You can't pull it out of the limit. The limit is dependent on n. Okay, but you can pull it out of the summation and put it right here. I'm not going to do that though. Okay, all right. So anyways, what am I getting when I distribute? So I'll get the limit of the sum of 52 n cubed minus 12i n squared minus 24i squared n minus 16i cubed, okay, all over n to the fourth. And then what you want to do is fillet all of this, okay? So chop it up into a bunch of little fractions, and then we're going to chop up the fractions into summations, okay? We know that this is finite, and whenever you have a finite sum, you're allowed to kind of play around with it and abuse the heck out of it with regards to notation. Usually have to be careful, because later on we're going to deal with infinite sums, and you're not going to be able to pull those tricks, okay? But for this case, if it's finite, it's just going from 1 to n, that's okay, all right? All right, so that's what I'm going to do next. I'm going to split it up so I have the limit as n goes to infinity of these sums, right? So the first sum will be 52 n cubed over n to the fourth. So that will just be 52. And then I'm going to factor out any constants. So, well, maybe I shouldn't do too much at once, right? So let me not then. All right, so the next one is then minus the sum of 12i n squared all over n to the fourth. Okay, and then minus the sum of 24i squared n all over n to the fourth. And then minus the sum of 16i cubed all over n to the fourth. Okay. And then all these sums depend on I, right? So anything that's not an I variable, you could treat as a constant and pull out. It's kind of like factoring, or reverse distributing, right? You just factor out anything that's not dependent on I. So in this case here, I'll have the first sum, I could factor out the 52, and I just have the sum of 1 from I equals 1 to n, and we have a formula for that. Okay, we're going to use the formula next. Okay, then minus, I could factor out, well, the n squared over n to the fourth is 1 over n squared. You could factor that out. You could also factor out the 12. So 12 over n squared, sum of I from I equals 1 to n. We have a formula for that, right? We have a formula for this, a formula for this. Then minus, I could factor out a 24 all over, it'll be n cubed times the sum of I squared. I have a formula for that. Minus this, I could factor out a 16 all over n to the fourth. And then I have the sum of I cubed, and I have a formula for that, right? Okay, so I'm going to apply my formulas for these. You don't have to have them memorized or anything. If you want to know more about those formulas, you can take a discrete math class. They usually talk about them there. Okay, so you get 52 times n times n. Well, it's just n, right? So it's just 52 times n. And it seems I've lost an n. It would be an n cubed, sorry, n cubed all over n to the fourth. This should be 52 over n. And then this will be 52 over n. And this is 52 over n times whatever is in this box, right? In this box, if you look in your notes, it's n. Okay. Then minus 12 over n squared times this thing, which is n times n plus 1 all over 2. And then minus 24 over n cubed times this thing, which is the long one, n times n plus 1 times 2n plus 1 over 6. And then minus this thing, 16 over n to the fourth, times this thing, which I remember is basically just this thing squared. Okay, so it'd be n times n plus 1 all over 2 squared. Ugh. Okay, what about these things then? These are easier than you think. They're all just ratio of polynomials. And if you recall, to determine a limit of something like n going to infinity of 9n squared minus 2n plus 1 all over 3n squared minus 2n plus 1. All you need to do is take the ratio of the leading coefficients. Okay, so this would just be 9 over 3, which is 3. So that's a shortcut. Okay, you have to be careful that you know what the leading coefficients are. So in the first one, what do we have? It's 52 n all over n, and that's just going to be 52, right? The n's will cancel, and you just have 52 for that part of the limit. And this is a limit as n goes to infinity. Okay. For the next guy, well, what about it, right? What is the leading coefficient of 12 times n plus 1? That polynomial. Well, it's just 12n squared, right? So it'll be 12n squared plus a bunch of junk, and then it's all over 2n squared. Okay. And then for my limit, I could just kind of pick off the high degree parts. Okay? And then minus, we have to be a little more careful here. The leading coefficient in the numerator, 24 times n times 2n. So it's actually 48 times n cubed plus some business all over 6n cubed. Okay? Then minus the leading coefficient of this thing is going to be, if you distribute and then FOIL, it'll be an n to the fourth times 16, so 16 n to the fourth. And if you don't believe me, FOIL it out and figure it out for yourself, right? And then I'll be all over 2 n to the fourth plus a bunch of business. Okay, and then I can, I have it. Basically, this is equal to 52 minus 12 over 2, which is 6, minus 48 over 6, which is 8, minus 16 over 2, 16 over 4, because this thing was squared, right? So it ended up being 4 times n to the fourth, which is 4n to the fourth. So 16 over 4 is 4, and let's hope we get the answer, right? So minus 10 is 42, minus 8 is, I believe, 30. This is the hardest part, right? If this is oh my God. Sorry. 52 minus 10 is 42. 42 minus 8 must be 34. All right, we got it. That's the answer. Okay, so brutal, right? A lot going on there. And I didn't really get good at this until after I took a discrete math class where they really focus in on summations, and you use them a lot in computer science too. So if you get the right teacher, um, and you take a lot of different math classes. So it's sad we don't have enough math classes where we work. But you go to Ohio State or probably somewhere like that, and they have all kinds of math classes you can take. Or you just watch videos online. You don't need to pay some guy. Watch tons of videos online. Go to the library, get some books. Just take them out, read them. And invest in your math education. Okay, it's better than other things. Some other things. Okay. Okay. We'll see you next time.